Hello, it's Mika. Today we're gonna do some more proofs on linear algebra, and today the topic is gonna be on linear independence, right? So we have a couple of facts, right, that are true, and we're gonna prove them to be true, right? So number one is any set of vectors containing the zero vector is linearly dependent. Number two vectors are linearly dependent if and only if one is a scaling of the other. And number three, if a subset of the VJs are linearly dependent, then the entire set is linearly dependent. So to begin, we should really understand what linear independence is, right? So in linear algebra, linear independence is kind of a way of saying that a set of vectors are all individually bring something unique, right, to this group of vectors, right? And the formal definition of it is that a set of vectors is linearly independent if the only way to combine them is to multiply each one by 0. To get to the 0 vector. And we can write this out as this vector equation ax equals 0, where A is a matrix, right? So we have this set of collection of m vectors, v1 to vk, and we can visualize A as v1, v2, ... vk. And you're multiplying that by x, and you're setting it equal to 0, right? So what you're going to have is x1 v1 plus x2 v2 plus xk vk equals 0. And what you're basically saying is that this equation can only be true or only be solved if it is the trivial solution, which means that every of the xj's equals 0, right? That's x1 equals 0, x2 equals 0, and xk, all the way up to xk equals 0, right? And that's basically the definition of linear independence, right? That the only way to get to the 0 vector is if every single vector that you have in this set is multiplied by 0. It's scaled down to 0, essentially, right? So once we know this fact that the solutions to this set, or to this equation for linear independence is that all the xj's must be 0, we can begin proving number 1. Any set of vectors containing the 0 vector is linearly dependent, right? So let's have our little set of vectors, x1 to xk, or sorry, v1 to vk. And let's write it out. x1 v1 plus ... xk vk equals 0, right? But you're saying that this set contains 0 vector, right? So we're going to let vk, because why not, be equal to the 0 vector, right? So this is 0. So you got x1 v1 plus ... xk times 0 equals 0. Now what we can see that is that any value of xk would actually work for this equation to be true. Xk can be anything. it doesn't have to be 0. And so by definition of linear independence, all of the xj's must be 0 in this equation for linear independence to be reached in the set. So if xk is not 0, then by definition of linear independence, the set of vectors v1 to vk is linearly dependent. All right? Okay. So let's go on to number 2. So we just proved number 1, right? So let's go on to number 2. And it reads, two vectors are linearly dependent if and only if one is a scaling of the other. So let's say you have two vectors, set v1 and v2, right? And let's assume that they're not linearly dependent, right? Which means that x1 times v1 plus x2 times v2 equals 0, where x1 does not have to be 0 and x2 also does not have to be 0, right? They both don't have to be 0 for this to, at least one of them doesn't have to be 0. At least one of them isn't 0, right? And so let's assume that x1 is the one that is not 0. So you can proceed with this some algebra to move this to the right side. And we can see that v1 equals minus x2 over x1 v2. Because x1 is not equal to 0, this is completely valid. And this just turns into the scale, right? So v1 is scaled by, so v1 is v2 scaled by minus x2 over x1. All right. And minus x2 over x1 is a completely valid scale because x1, as we said, is not equal to 0, right? By definition of linear dependence. Okay? So we just proved kind of like the first part of that, but this one goes both ways, right? It's got this sign, so we also have to kind of prove the other one. So if the other one is that if one is a scale of the other, if one vector is a scale of the other vector, then they are dependent. Okay, so we have v1, let's start with the same thing, v1 equals, let's give this x 2 v2. All right. So v1 is a scale of v2 by x2. And v1 minus x2 v2 equals 0, right? And then we have 1 times v1 minus x2 v2 equals 0. This is true, right? So we can see that we can add a plus here. All right, we can see that even if x2 equals 0, we still have a non-zero coefficient of v1, right? Which means by definition of linear independence, this set of vectors v1, v2, where v1 is a scale of v2 by x2, they are dependent. All right, perfect. So we proved it both ways, right? So the first one, we were proving that if v1 and v2 are dependent, then one is a scale of the other. Are dependent, then they are scales. And the other one is if they are scales, then they are dependent, right? So this is part 2. And it goes both ways. All right, so we got that one. Check that. And the third one is if a subset of the VJs are linearly dependent, then the entire set is linearly dependent. Okay, so let's get a new page. So let's say we have a set of vectors v1, v2, v, let's call it n. All right. And then we have a subset. All right, what does the question ask? If a subset of the VJs are linearly dependent, then the entire set is linearly dependent. Okay, so let's say we have a subset of that, and we kind of take v1 up to vk. So we have v1, v2, vk, which is a subset of v1, v2, vn, because k is less than n. Right? So this we find that or we can call this VJ actually, right? Just to make it a little easier. So VJ. Okay. So we find that if this is our subset v1 to vk, and this is our overall set v1 to vj, then we're talking about the subset v1 to vk being linearly dependent, right? And that means that they would satisfy this equation plus xk vk equals 0, such that one of these is not 0, right? It could be x1, x2, all the way up to xk. One of them doesn't have to be 0. But the only way that they'd be able to satisfy this equation is if one of the vectors is a 0 vector. So let vk be equal to 0, 0 vector. Right? So now, if vk is a 0 vector, and then xk can be anything, right? It's the same proof as number 1. So if v1, v2, up to vk contains 0, then the superset v1, or the overarching set to vj, also contains 0 vector. And this means that the whole set v1 to vj is linearly dependent by proof number 1. Right? So that's the proof. Basically, we found a subset of the superset v1 to vj, and we call that v1 to vk, so this is our subset. And that is in v1 to vj. And we said that if this to be linearly dependent, then vk is going to be the 0 vector. We just label it that, right? And if it's a 0 vector, then xk can be anything. And if xk can be anything that's non-zero, then this subset is linearly dependent. Since this subset, we proved that this subset is linearly dependent, or we showed how by including the 0 vector. And so since the subset is part of this overarching set, then the zero vector is also part of this overarching set, which means that by the same logic, the big set is going to be linearly dependent because it contains a zero vector, right? So that's the proof number 3. Check mark. All right, that's it. Thank you for listening.